tous la bienvenue dans le cycle de conférences que Redouane Qara a initié. Donc, on va essayer de commencer un cycle de conférences. On va essayer d'être le plus régulier possible. On espère le faire chaque semaine si on arrive à avoir beaucoup de conférenciers ou là, sinon au moins une fois tous les 15 jours. On va essayer de profiter des connaissances de nos collègues installés un peu partout. Donc, aujourd'hui, j'ai le plaisir d'être celui qui va vous présenter la conférence d'aujourd'hui. Donc, je ne devrais pas présenter Professeur Bettayeb, mais je vais le faire pour les gens qui ne le connaissent pas encore. C'est un professeur qui a formé pas mal de gens à Tizi-Ouzou. Donc, je vais commencer par sa biographie. Sachez que Professeur Bettayeb a été formé au lycée polyvalent de Tizi-Ouzou, pour les gens qui connaissent la ville de Tizi-Ouzou. Il a eu son baccalauréat en 1972, avec sa mention très bien en mathématiques. Il a eu une bourse qui lui a permis d'aller poursuivre ses études à l'Université de Californie du Sud, à Los Angeles. Il a réussi à avoir ses diplômes respectifs de licence, de maîtrise et de doctorat, 76, 78 et 81 respectivement. Il a travaillé une année dans le centre de recherche polaire de Sharjah Development Company, à Houston, au Texas. Il est rentré au Zaïre et il a été installé au CDTA, donc, où il était directeur du laboratoire d'instrumentation et de contrôle de 82 à 88. Le Hajj Bettayeb, il a corrigé. En 88, il a immigré le Saoudi. Il a rejoint l'université KFPM, c'est King Fahd University of Petroleum and Minerals, في دهران في السعودية. Donc, il a travaillé 2 années. Même en 2000, il a rejoint l'université de Sharjah, en tant que professeur, où il a entamé il a passé tout le reste de sa carrière. Il a occupé plein de postes, que ce soit administratif, mais la plupart des postes qu'il a occupés, c'est des postes de recherche. Et en 1994, donc depuis septembre 1994, il occupe le poste de vice-recteur et il fait la graduation. Donc, il était chargé de la graduation et la recherche fait Jamiat Sharjah. Il faut savoir aussi que Professeur Bettayeb est également professeur associé au centre de recherche CUIC, le King Abdelaziz Université, dirigé par notre ami Obaïd, qui est parmi nous l'homme. Et voilà, donc il est professeur associé. Donc, durant toute sa carrière, Cheikh Bettayeb, comme j'aime bien l'appeler, il a publié plus de 350 publications dans le domaine du contrôle et du traitement de signal en particulier. Il a également supervisé plus de 50 thèses de doctorat. Tout au long de sa carrière, donc, il a largement contribué pour son travail sous forme de prix d'honneur. Allah يبارك, il y en a beaucoup. Je ferai une conférence à sa place. Donc, يسمح لي Cheikh Bettayeb, je ne vais pas toutes les citer, mais masha'Allah yani. Celui qui veut savoir on a mis tout ça sur le site de l'université, donc vous faites www.mto.tz, vous trouvez sa longue biographie. Concernant ses relations à Tizi-Ouzou, Cheikh Bettayeb, il a d'abord connu notre mentor, Cheikh Kamel, Cheikh Saad Jennoun, au CDTA, où il était son directeur. Même d'après, Saad, il a rejoint l'université de Tizi-Ouzou. Et Cheikh Bettayeb, personnellement, j'ai connu en 2006, qui l'a invité pour présenter une conférence en 2006. Et c'est depuis que j'ai le privilège de connaître donc Cheikh Bettayeb. Et il était mon directeur de thèse. Et sous la direction de Saïd, ils ont encadré à peu près une trentaine de thèses de doctorat à Tizi-Ouzou, dont 15 ont été soutenues. Donc, il a soutenu au moins 15 thèses de doctorat à Tizi-Ouzou, dans la faculté. Je vais vous raconter une dernière anecdote. L'âme l'oul, en 2019, je suis allé sur le site Scopus, la base de données Scopus, pour voir un petit peu la production scientifique de l'université Tizi-Ouzou. J'ai trouvé que Saïd Jennoun, il a participé à la publication de 72 articles في Tizi-Ouzou. Et juste après, Cheikh Bettayeb, il vient avec 69 articles. Donc, ce qu'il faut savoir, c'est que sur 69 articles publiés في Tizi-Ouzou, 69 منهم, sur la plupart des publications sur Tizi-Ouzou, il y en a à peu près 900. 69 ont été dirigés ou co-écrites par le professeur Bettayeb. Donc, masha'Allah, cela a contribué énormément à la formation de nos docteurs. Donc, il y en a واحد منهم. Et j'espère qu'on va continuer à former la prochaine génération. Donc, prenez autant que vous pouvez de Cheikh Bettayeb et profitez. Aujourd'hui, il va nous présenter une conférence donc, sur l'automatique qu'il a intitulée donc, la présentation d'Arolium, c'est Automatic Control, State of Art and Future Direction. Donc, il va nous faire l'état de l'art sur le contrôle des systèmes, l'état actuel, donc l'état de l'art actuel et probablement des directions futures pour les gens qui veulent de la recherche. Donc, sans plus attendre, je vous passe la parole, M. Bettayeb. On vous écoutera avec plaisir. À vous la parole, M. Bettayeb.
Barakallahu fik, Rachid. Je vous remercie. Bismillah. Assalamu alaikum. Good afternoon, everyone. It gives me a great pleasure to be with you. It is an honor to be associated with University Mouloud Mammeri de Tizi-Ouzou. And it is my pleasure to share with you today what is going on or what has been going on and what people are thinking about research in automatic control. Rashid, everything is clear? Are you?
Yeah.
Okay.
Tu mets barque la présentation.
Yes. Yes. Okay. Okay. So, today I will talk about the field of automatic control, the status of automatic control these last few decades, and then projections into the future and application areas. So I will motivate the importance of automatic control in the beginning, and then talk about challenges. And then I'll mention what kind of techniques in advanced control are partially solving these challenges. And then I will talk about present and future trends of automatic control with the various potential applications that we'll be working on. So, of course, control and process control in particular is very important. With introducing control in a plant or in a process will increase productivity, will give a better quality products, and will optimize the utilization of the raw material in the loop, and it will save in energy and of course have a safer environment and do better energy integration. Of course, there are many benefits of control. Once you introduce a control loop for process variables in any plant or system or process, with the tight control and optimization, you get better product quality. You get better profit because you gain in energy consumption and others. You get better service quality because you are maintaining the variables at the nominal values, and therefore you produce what you want with the quality needed. You enhance the plant operation. You extend the life of the equipment because you would like to develop smooth control so that the equipment actuators are smoothly operating and safely, of course. And then you improve the performance of the system output. You reduce the consumption and you prevent accident. So what is it when we have a control loop or a process control system? What are the challenges? Many challenges. very, very difficult challenges. We have time delays in systems. And you have a delay, therefore you will not be able to reply or control the system or correct or compensate for the system before you see the process variable or the output. There is some crazy non-minimal phase behavior that we don't have time maybe to explain, but anybody is welcome to ask me later questions. We have complexity in modeling. We have physical systems that dynamic behavior depend on space and time. We have uncertainty in process variables. We have fluctuations in raw material. We have all kinds of predictable and unpredictable disturbances. We have variables you cannot measure in some applications, such as space, nuclear, chemical, etc. We have process hard nonlinearities that is difficult to develop controllers for them. You have constraints on variables, and you have interaction between processes, loops that make life difficult to control the various variables. And you could have multiple timescales, as I will show in a few minutes, some examples. Of course, an example of these challenges for solar photovoltaic and wind turbines is, as you know, you don't get the sun or the irradiation or the wind the time you want, at the pace you want, with the amount you want. So especially wind, there is a lot of randomness and unpredictability in the wind. So the control loop has to deal with that. We have inherent complexities in wind and solar and fuel cells, nonlinear dynamics, etc. We have changing dynamics. Things change with time, and sometimes unpredictably, sometimes randomly, sometimes you don't know this change. And for wind systems, these are large structures that could have a big complexity, and therefore the controller has to be able to cope with these complexities. Just to give you a concrete example, in renewable energies, you have, look at this, this is power demand, for example, typical, but look at the irradiation you are getting, the solar irradiation, very random, unpredictable, variable. This is for one specific day. The next day it will be something else. The other day it will be something else. Next month is very different. So solar irradiation is not something you control, while the control loop has to cope with all of this. Same thing for wind. Look at this variability and unpredictability of the wind speed in a given day, or next day it will be something else. And again, all these energy consumptions are affected by the temperature profile. And again, temperature profile is also partly unpredictable and variable, very variable. Other problems is the multi-time scale behavior I mentioned. You could have systems where your controller has to cope with phenomena changing in seconds, with seconds behavior, and phenomena changing in minutes and hours, or picoseconds sometimes. Here is an example of fuel cell. There is an electrochemical dynamic behavior, a mass flow behavior, and thermodynamics behavior. And all of you know that thermodynamics are slow. It's in minutes. Look at this. It's in minutes, sometimes in hours. You know, behavior, physical evolution of thermal behavior. So can be in seconds and minutes, while the mass flow could be in milliseconds, while electrochemical dynamic behavior could be in picoseconds and less. So your controller has to be able to follow the behavior of all of this. The behavior of all of these timescales, and it's not evident. Could you imagine you are controlling a variable that is changing every minute, and another variable that is changing every picosecond. It's not trivial how the controller will do it. Very, very difficult. So these are timescale problems. Further, you could have a multi-level control with some hierarchy. 3 famous hierarchies: primary control, secondary control, and tertiary control. For example, in a microgrid or in many, many applications, in any power systems, you have this 3 level, the local level, the secondary level, and the management level up there. So all of these have to be interconnected, coordinated together, and the controllers at every level are different, and they have different challenges. And to solve all these problems, many advanced control technologies or techniques have been developed, such as multivariable control, decentralized control, optimal control, model predictive control, robust control, fuzzy logic, neural network, all of this. So all of this partially solved. For example, multivariable control is good to solve systems that are interacting. Decentralized control is good for multi-loop systems that are weakly connected. Optimal control, you are optimizing something, etc. So every one of these solve part of the problem, but as we say, there is no free lunch theorem. There is no one technique or technology that works for all or does very well for all. So to give you an example, so people are trying to see what is the present and future impact of closed loop control, of automatic control in the industry. And this is a survey that was done by many famous industries such as Honeywell, Yokogawa, Leeds and Northrop, all of these major companies in process control. And the question was asked, what is the current impact of the famous control technologies? What is the current impact and future impact the next 5 years or so? And let me give you the conclusion of this. The conclusion is PID has been dominating for the last 50 years. Proportional integral derivative control, the simple PID, is implemented in every single loop in the industry. But in the future, it will be replaced by the famous predictive control. Model predictive control came in the 80s. It's penetrating strongly, trying to slowly replacing PID. And the next 5 years, it will replace a lot of it, and it will continue to replace. The others, even though all of this, and most of you know all of this, adaptive control, robust control, nonlinear control, they have been there for a long time, but they are picking a bit, but not enough. A bit more specifically, here is an example of the different survey for 3 industries: the process industry, the aerospace, and the automotive. And again, it confirms the same prediction for the near future. Here it is, MPC, model predictive control, is going to be dominant now and in the future compared to robust control, which is not picking up, compared to adaptive control, which is not picking up enough. Same thing for nonlinear. As you can see, model predictive control is going to be the future. If you want to contribute to the industry, work on model predictive control and related issues. There are other issues, of course, theoretical, but MPC, if you can do any improvement in MPC, it has a chance to be implemented in the industry. And of course, as we mentioned, with all those challenges, you may have a physical system whose model is known, And this is called white box model. So from the physical, chemical, mathematical laws, KCL, KVL for electrical, couplers for aerospace, Schrödinger, Maxwell for antennas and other applications, telecom, thermal, heat equations for thermal processes. You can write the partial differential equations or differential equations, and that's what we call white box. The model is completely known. And you can develop a model predictive controller on that well-known model. But there are physical other processes for which you have no idea about the model. The model is unknown. You have input-output data. And this is called a black box. And you need to develop a model predictive controller technology that is based on input-output data, not on models. And again, if sometimes you have, maybe you have differential equations of the physical system, but some of the parameters of are unknown, and therefore it's called in between black and white. It's called gray box model. You know the structure of the physical system, but model, but you don't know its parameters. So you can see the challenge you have for every technology. Let it be model predictive control, let it be adaptive control, let it be robust control. You need to develop possibly three different types of controllers for the three possible behaviors in physical reality. And one promising area for black box control or gray box control is active disturbance rejection control. You have a process, it has internal disturbances, uncertainties, parameter variations, and non-parameters. They are all here. And you have unpredictable external disturbances. So what do you do with this famous ADRC, active disturbance rejection control, which is relatively recent, developed by Chinese Han, Professor Han? You estimate this and this together is called total disturbance. What is total disturbance? Anything you don't like, anything you don't know, anything unpredictable. Let it be time-varying behavior, nonlinearities, constraint, process nonlinearities, internal disturbances, external disturbances, uncertainties. All of them are in here and here. You put them here from the input-output data you can get from your process. You estimate this, all these uncertainties. Once you estimate them, you can correct, compensate for them through a controller and control this overall system. And you have control a process. You don't know the model. I didn't assume anything whether this model is what a certain type of differential equation or so. So this is black box, but also people developed ADRC for gray box model, where you have some partial knowledge of the model of the process, and you can incorporate it here and in the controller design to develop a closed loop control. So let me give you, since I said this is state of the art, I'm gonna report two findings, two big studies worldwide made by world authorities in control. One is done, this one is done in 2003, and the other one is done in 2017. So this one is done in 2003 by all the famous world authorities of control. Professor Murray from Caltech was editing this 100-something pages report. Its summary was published in IEEE Control System magazine in 2003, 2004. And with him, all those famous people, Carl Armstrong, John Doyle, Cargonecker, just name it, all the famous people were here to talk about the existing technologies of control and what should be the next 10 or 20 years, what should be done in control. So they identified these important areas of control, which are aerospace and transportation, information networks, robotics, intelligence system, biology, etc. And they developed these challenges and opportunities for the next 20 years at that time. And here is what the opportunities were: control, emerging control applications are here, where control theory has room to make things, success stories happen in these areas: aerospace, robotics, networks, materials, economics, biology, smart engines, as you can see, all kind of applications. Here are examples, all kinds of examples, from robotics to smart structures to sensor networks to traffic, just name it. And here is the summary of future directions they developed out of this 3 years study of 20 world authorities in control. And so they gave 5 recommendations. The first recommendation was to increase research by integrating control, computer science, and communications. And you have seen this the last 20 years with network control systems, with so many other things that I will mention in detail later. Increase research in control of high-level decision-making. Yes, control is entering many things, many areas of decision-making in energy, in transportation, in smart cities, etc., etc. Long-range applications, theory, applied mathematics, more and more applied, and in education. So that was the first study. The second study was done 14 years later. 14 years later, some of the same people, such as Moray, Cargonekar, and others, these people, you know them, developed also, worked for 2 or 3 years, and wanted to develop what is the present status of control and what are the next challenges of control so that it will impact humanity. Control theory should contribute and impact humanity. So it was published in annual reviews in control in 2017 by these same people who were forming a group in the IFAC, International Federation of Automatic Control. And here is their finding. Their finding, they say, all right, most countries in the world, they have what we call Horizon 2030. And in this Horizon 2030, with some variability, most people, most countries in the world, they have these 5 critical themes or target areas or priority areas or critical societal challenges. Most countries have this: transportation, energy, water, healthcare, manufacturing. Okay. Some of the people have 7. Space, they put it separately, while here it is here. Other people, they put education separately, etc. So in these 5 critical themes or priority areas for most countries in the world for the Horizon 2030, this group developed 7 key research and innovative challenges where automatic control can make breakthroughs in these areas the next 10 years, let's say. The next 10 years, of course, it will continue. And these areas, again, this is from the last report also, distributed network control system, and I'll show you some block diagrams, data-driven dynamic modeling that I mentioned related to active disturbance rejection control, complexity and control, because systems are becoming more complex, so people have to see the relationship of control and complexity, critical infrastructure, cyber physical systems. Physical systems are being interconnected via control, sensing, communication, internet, and therefore you have to ask yourself the cyber security aspect. autonomy, cognitive and control, all these space shuttles, robot networks, etc. And the human, the loops with the human behavior and cyber physical systems. And then within this, they identified 22 application areas where control really can do important contributions. And I'm sure most of you are working in at least one of these, where really control can make the difference and serve humanity. Road and air traffic, automotive control, railways, space, marine, renewable energies, smart grids, energy efficiency, distribution networks. See, all of this from all aspects: health, logistics, high-tech technologies, mechatronics, smart cities, buildings, social networks, financial markets, and the role of IoT, Internet of Things, that I will elaborate a bit later. So these are the areas where control can make important contributions to humanity in the next 10 years. And they developed some 20 questions of things we should do. We researchers in control should be replying or answering the next 10 years through our research. How to design control for network over wireless communication, how to design control algorithm, how to ensure security, etc., etc. So many, about 20. All of these are important questions to answer, and people are working in these areas. All right, so let me summarize what was said, plus project on some of the specifically areas that people started to work on in research and development, and they will be here for a long time because it's barely, some of them are barely at the laboratory level, and a lot of work the next 10, 20 years needs to be done. And I will mention the consequences of this on we control theorists and engineers, what we should do in this area of control theory and applications. So again, we continue integrating control, computing, communication networks. Fault-tolerant and reliable systems is becoming more and more important because now physical systems are complex and you cannot make a simple diagnosis. So you do have to develop controllers that are fault-tolerant and they are reliable. High-level control for decision-making for the same reason. Now you have enterprises that are doing things across countries, across continents, and you have to make decisions in optimization and control, and therefore control will play an important role. You have wireless sensor networks, network control systems, Internet of Things control systems. I will give examples of this in a minute. Cloud control systems, dependable control systems, digital twin control systems, and combinations of this. I will give some examples of this as we don't have time to cover all of them. So here is an example of the famous network control systems. You have a plant in Tizi-Ouzou. The actuators are in Tizi-Ouzou, the sensors are in Tizi-Ouzou, but the controller could be in Algiers or Tamanrasset, right? The controllers. Through internet, you control, these controllers control this important process that is Tizi-Ouzou. For some reason, for a reason that I will show later, that you could have many plants with many controllers and they cannot be in the same place. The controllers, you need to do possibly calibration of the plant, you need to do maintenance. I have seen it myself, this kind of configuration over 20 years ago, well, 17 years ago. In 2002, 2003, I was a visiting professor at Helsinki University of Technology in Finland. I used to go every summer there to teach Nokia engineers give them MS and PhD courses in control and signal processing. And from Helsinki, we were controlling, they took me to the control room where they were controlling from a control room in Helsinki, a plant, a transformers 1,000 kilometers north of Helsinki in the middle of a forest. So these physical systems exist, and sometimes you need to do that. Through this controller, you maintain the variables, you do maintenance, predictive maintenance, you do calibration, you tune the behavior of your processes, etc. From Helsinki, where the plant is 1,000 kilometers away. Of course, the system could be more complex than that. You have a network and you have many plants, many physical systems, and many controllers. How are they connected here? You may have a plant, an actuator, a sensor, a plant, many control loops, 1, 2, 3, 4, all of these control loops, actuator, sensor, the plant, many control loops, and one controller controlling all of them, all of the control loops. This is called centralized control. Well, you could have a decentralized control for every control loop, sensor, actuator, controller. And you control this loop, another loop, and they are disconnected. And therefore, it's decentralized configuration. And if they are connected together, the loops are connected together, it becomes distributed control. So all of this exists in real life. Of course, this creates huge, many challenging problems that every one of us has room to do research on this. Every one of these items, hundreds of PhD theses will not solve them yet. I supervised myself in some of these areas, MS and PhD theses, but it's only the beginning. So you have packet dropout. You are sending a signal from a controller to a plant through a network. So there may be congestion, and you lose some communication data. You have network security. Is your data going to the right place, or is it disturbed and changed? You have sensor failures, actuator failures, you have quantization, you have uncertainties, you have delays in the network, you have queues, you have latency. All of these are very challenging problems. You have to generalize control theory to control theory with delay, with packet dropout, with quantization, with disturbance, with scheduling, with security. So all of these are challenging problems, and hundreds and thousands of theses and research articles are being published the last 10, 20 years, and still it's in infancy. It's only in the beginning. It's only in the beginning. All right, now, so these network control systems created new theories of control, because it's network control systems. You are controlling over network. You send data. By sending data, it's going to be packets. So just pure continuous control will not work. You are digital through networks. So you have to develop a new theory, switch systems. You have to generalize. You have to generalize linearity, nonlinearity, robustness, stability, controllability, observability, all of this to switch systems, to Markovian systems, to impulsive systems, because this kind of behavior exists in a network control system, an input delay, etc. So all of these are new. There are now books and hundreds of theses. I have myself 3 books on impulsive system, 4 or 5 books on this. Many work has been done in these areas. So all of these are generalization of classical control theory, and they are still open, many open problems. Now we can go even, this is new. This is really at barely a laboratory level. Few big companies such as Honeywell are starting to implement. So this is the future of the process industry. It's called cloud control systems, because now many universities are connected to the cloud for all these systems, and many industries are connected to the cloud. Many enterprises are connected to the cloud. You don't need just your bulky servers everywhere around you, but you get time and space in the cloud, and you do computing, you do control, you do processing, you send data, you receive data, you check your security, cyber security, etc. So, and therefore, in this network control system, there are control loops, there are sensors, actuators, and therefore you have your controller possibly in the cloud, and the controller develop its algorithm in the cloud, and you end up with the cloud control system. And you can see what is involved. The controller is involved, the cloud, the complex system, Internet of Things, because there are sensors and actuators. I will mention later. So the bulk of all of this that made it happen is what we call the IoT, the famous Internet of Things that appeared some 10 years ago or so. And now it's making a revolution. Today, they are saying there are 50 billion items connected together in the world, and it's growing exponentially. Sensors, actuators, smart cities, transportation, they are all connected together through what we call Internet of Things, through an internet, through a communication channel with sensors, actuators, data, computing, cloud. All of these are connected together for certain applications, 50 billion devices are connected. So that is the future. And some of them you need to do control, you need to process data, you need to model, you need to diagnose, you need to forecast, you need to predict, you need to identify, and therefore control is involved. So as I mentioned before, here it is, the controller is in the cloud. So you have controller in the cloud, and you control your control loops from the cloud. More than that, this is also at the laboratory level, what we call dependable control system. You have your controllers in the cloud, you have your control loop, you have the Internet of Things networks that allow your sensing and actuating, and online, maybe real time, you receive all kind of data, temperature, weather conditions, earthquake conditions, all kind of conditions. And based on that, on temperature irradiation, you use the right controller to track the solar tracker, the solar cells. And depending on the situation, a certain controller in the cloud is ready to be optimized to track optimally your solar cells or your solar panels. More than that, you can do what we call efficiently use controllers. You have many processes. You could have one controller controlling all these processes, different plants, difficult physics plant in even different continents, and possibly the second controller, if it's not controlling this plant, it's redundant to this plant. So controllers at any time, they can be ready to be used to control and be redundant at other times. So with few controllers, you are gonna able to ensure high efficiency of using the resources while keeping safety with the redundancy. More than that, you could have even, this is new, this is very new. It's not even implemented yet, but at theoretical level now, people are developing many of this. You have loops, and you have three types of loops. You have an active loop, you have a loop that is active, you have a loop that you don't need anymore, you disconnect a loop, and a loop that is possibly standby, ready to use. So you create loop, it's flexible. You are creating loops, you are eliminating loops, you are adding loops. So you could really optimize a lot of control. And here is an example for renewable energies. These things are happening now with cloud computing. You use controllers, and through Ethernet, you control all these renewable energy systems. Of course, the control of Internet of Things will impose so many challenges. So you are controlling over non-deterministic networks. You have a latency and jitter. You have high bandwidth. I mean, with the Internet of Things, they're not only sensors and actuators, they are audios, videos, images that you are going to send to different places. And therefore, you need high bandwidth. There is a big challenge with sending videos in seconds or milliseconds. And the security aspect, you are dealing with data, so you need to make sure you are solving the security aspect. So all of these are affecting your control loops, and therefore you need to generalize classical control theory with control theory where in the loop you have a stochastic network that is sending and receiving data, there is a queue and delay in your sensing. You need extremely high fast speed to process in real time your images and videos, and you need to be secure and safe. So all of these are big challenges for control theorists. And because of this, the conclusion of this talk is going to be as follows. It's not anymore control theory alone. It's a really multidisciplinary areas. It's control theory with computer science, with mathematics together, that they solve all these problems. Control theory, communication theory, programming, all of this together to solve all these problems. Now, you have a very complex system through the internet with IoT. You need communication people. You need computer scientists for artificial intelligence, for deep learning or machine learning, to process that data and organize and then predict the forecast, etc. And you need control theorists for the control loop. So all of this now, there are people who are claiming nowadays, they are saying we should teach control theory and computer science in high school. There is a book that just came out. It's called Control Theory in High School. There is another book, Control Theory for Everyone. So nowadays people are saying, hey, listen, control theory is a must because 50 billion devices are connected through the internet. Therefore, whatever you have at home, whatever you have in your mobile, whatever you have in your car is connected to this. If it is connected to this, to be able to use it or understand it, whether it's done optimally, these control theorists, they have to understand computer science, artificial intelligence, machine learning, optimization to be able to do this. And therefore people are claiming as mathematics now is basics, physics is basics, biology is basics. Now control theory should be basics in high school and computer science should be basics in high school. This is a thing that is recommended by many people nowadays. The last thing, one of the last thing I want to cover, because we are running out of time, is what we call digital twin. So now with this Internet of Things, you can have a physical plant, a physical process, such as this gas and oil installation, and you duplicate it through virtual space, and then you can do all kinds of simulation, prediction, forecasting, scenarios, anything you want. This is called digital twin. You create a twin. And thanks to Internet of Things, IoT, because you're gonna need sensors coming from the physical plant to go to the virtual, and then signals are sent. So you are doing IoT with digital twins. So this is just a detail. And this is just to tell you that digital twins are already implemented. This is an implementation in some wind farm. I don't want to go through this detail, but digital twins is coming very strong. It has many advantages. And this is what many important famous companies in the world are saying. It is predicted by 2022, just in a year and a half or a year, over 2/3 of the companies implementing IoT will have deployed a digital twin solution into the production of oil, gas, solar, transportation, just name it. So it's next in the corner. So it's good for us that some of us start doing research in this area, meaning control within the Internet of Things, cloud control and network control systems, etc. And the last thing I want to mention is all of this is done in the context of the fourth industrial revolution, which is Industry 4, which we are living today, which is the combination of industry, automation, digitization, and current Internet of Things all together to connect the whole world and do whatever is needed. With this, a plant in Brazil is controlled from Finland or from anywhere in the world. Of course, Industry 4 has all of these areas we mentioned, that I mentioned many of them: Internet of Things, cloud, integration, decentralization, robots, all of these applications. And every one of these needs a lot of control and signal processing research to develop in this area of Industry 4 or fourth industrial revolution that just came, and we are living for it, that will stay for a long time. As you know, every industrial revolution stays for a long time. Some of them stay the century or the 60 years. So this will be with us for the next many years, yes, or a few decades, yeah. Okay, these are applications. I think I will have to stop here because we are running out of time, and I'll be very happy to answer any questions you have. Thank you for listening. أيوة رشيد رضوان.
Merci Cheikh Bettayeb pour la présentation. Rachid, allez.
Je vous remercie, Cheikh. Barakallahu fik, Cheikh.
شكرا.
شكرا جزيلا. Je m'adresse donc à l'assistance. S'il y a quelqu'un qui veut poser une question, donc soit il le fait, soit il m'envoie un message à travers le chat et je peux poser la question à votre place.
Cheikh Rachid.
Oui.
J'ai une question par rapport aux jumeaux numériques.
Ok, tu poses ta question.
Donc, c'est par rapport aux jumeaux numériques, pratiquement, c'est les derniers slides.
Oui.
Donc, Cheikh, quand vous parlez de jumeaux numériques, alors là, j'ai vu ça dans des systèmes à événements discrets, les systèmes manufacturiers, où on construit des jumeaux numériques pour des systèmes qui existent. Mais dans le domaine continu, je n'ai pas encore vu une application de jumeaux numériques pour des systèmes continus. Je ne sais pas si vous avez une idée ou là. Est-ce que vous avez une idée par rapport à ça ou pas?
Ça a coupé, la connexion, ça a coupé. Vous pouvez répéter, s'il vous plaît?
Cheikh Bettayeb, par rapport aux digital twins. Digital twins, les jumeaux numériques.
Oui, oui.
Alors, d'habitude, on voit ça dans au stade de la simulation, dans des modèles à événements discrets, des systèmes manufacturiers par exemple, ou des systèmes de transport, mais on ne voit pas ça dans les systèmes continus.
Et la différence maintenant, c'est avec l'introduction de Internet of Things, donc le twin, il est directement connecté. Let me speak in English just in case there are people from, yeah. So the difference is now, because we have Internet of Things, sensors continuous and discrete sensors and actuators are connected via Internet of Things and networks from the real system to the twin, and therefore we will be able, through the cloud or Internet of Things, to do all these valid for both discrete event and basically continuous systems which are sampled, of course. Yes.
Yes. Merci.
Moi, j'ai une autre question, cher.
Yes, please.
Est-ce qu'un jour, l'être humain peut être un élément à contrôler sur le réseau pour ne pas endommager le système? Parce qu'il va faire des bêtises, il va faire n'importe quoi. Est-ce qu'il ne peut pas être un jour élément à contrôler sur le réseau et non pas un élément de contrôle du réseau?
Yes, this is, by the way, they are talking about it. So the question is, will ever one day we'll have a human as part of the loop or the network? And the answer, yes, there are a lot of research going on. Human in the loop, human in the network. So yes, at least from an artificial intelligence point of view now, the people are modeling the behavior of the human, and via artificial intelligence, deep learning, and data sciences, they are mimicking the human being and definitely putting it in the loop. So there is a lot of research going on this. And so that's why, yes, many people are saying life will be different, control theory and life in general will be different 20 years from now. We'll think differently.
Yeah.
You know, some people are doing, I remember 5-6 years ago, I was reading some papers. I gave one of them as a graduation project. What is it? Affective signal processing. You see, you get a signal of الحساسية, الحساس, the senses that some person. So yes, a lot of things. The future, there are big challenges that people are thinking to work on, because we have all over the world many smart control theorists like you guys who can do a lot of good work. Yes, there are success stories on this, but it's in the very beginning only.
Yes. Une autre question, cher.
Yes.
Si je suis étudiant à Tizi-Ouzou, comment je peux participer à résoudre un de ces problèmes?
OK. Donc, la meilleure solution, c'est de faire un premier... Si vous connaissez quelqu'un, if you know somebody, if the student knows somebody at Tizi-Ouzou, maybe he can guide him in the beginning. If he doesn't, I think the internet is a good thing. If he goes to Google Scholar or Scopus, there are ways to find groups all over the world working on that specific area. He can do a reasonable search in Google Scholar or Scopus, where he can really find the clusters of research scientists working in that area. Of course, if it's anything related to these areas, I'll be very happy to help, because if something I cannot do, I have a big network all over the world, so I can at least help. But this is the way to start. With Google Scholar, you can kind of find some research groups working in that area, and then once another thing you can do is put some keywords and find few review survey papers in this area, and in these survey papers or review papers they call them, just write, for example, cloud control system review. If there is a review paper in that area, the review paper will overview for you 120, 150 papers of the last 10 years in that topic. And then by reading that review paper, you will find what we call a research gap, a research gap. You will find a gap. You say, people did this, other people did this, other people did this. But the time delay was not taken into consideration. The jitter was not taken into consideration. Here, I have a direction. That's my PhD thesis, etc. Research gap. From every review paper or survey paper, you will find many research gaps. Some of the authors, at the conclusion, they even put future work. And then you will be able to identify. What's good about it is you with your background or student with his background will see things differently than the authors who wrote that paper. And therefore, he will be able to find a direction that could be unique to him with his background. So the student should not be discouraged. He will think that, oh, 5 famous authors developed this review paper and they know all the gaps there. No, no. Everybody sees things differently. And with your background, you can find a niche, a direction for yourself that you, with your background, you will contribute, and probably other people cannot contribute because they don't have your background. So it is possible. It happens to me. No problem. It happened to Rashid with me and others.
Yes, thank you. Do you have any other question? Okay. Dr. Obaid, have you a question to Maamar? Or Mariam? Or Fazia? Any? No question. OK. Y a-t-il quelqu'un qui veut poser une question? S'il ne veut pas la poser directement, il peut la poster. Je la ferai avec plaisir.
Fazia, elle veut poser quelque chose. Okay.
Fazia, تحشم.
Il y a une question en message, M. Moussouri.
Vas-y.
Activez son micro.
Par message.
What will be the role of... OK. I'm read it. Sheikh Bettayeb, what will be the role of nanotechnology in the evolution of the control systems?
Yes, yes, nanotechnology is one of the areas determined from this panel in 2017. I mentioned, yes, you know, nowadays you are producing new materials for many different applications. People are developing, are designing nanomaterials for applications in energy, applications in dentistry, you know, for tooth. In energy, people are developing a new material, nanomaterial, to put on top of the solar cell so that, for example, the dust will not, the dust of humidity or humidity will not stay there. And the nanomaterial can kill it. So when you develop this, you develop a model of this nanomaterial and you look at its dynamic behavior, you are gonna do modeling simulation, and you may have to do some control of some process variables there. That is the quantity of the nanomaterial you will do. There are control loops in nanomaterial processing, they call it. Yes, many, many applications in energy, in dentistry, in health. I have in our university a big research group of 15, 20 people doing nanomaterials with background in chemistry, in physics, in engineering, in dentistry, in health, in medicine, in pharmacy. People are introducing nanomaterial in pharmacy, in dentistry, in energy, in PV, etc.
Yeah. I have another question.
Yes, please.
From Miriam. Thank you. Thank you, Miriam. What is the position of control theory with respect to the artificial intelligence development?
Yeah, that's a good question. Now, look, with control theory, you can do optimal design. Now physical systems are getting much more complex and bigger, interconnected, multidisciplinary. So it will be difficult to develop control design based on classical design. You write differential equation, you get a model. Based on this model, you develop LQR or LQG or robust control, or it will be very difficult for these hundreds of interconnected multidisciplinary systems. So for this system, you use data. Based on data, directly you develop the controller. Now, the data is raw material. So via artificial intelligence, deep learning, machine learning, you organize that data and then you tailor it towards controlling your process. So basically, you know, it's a modern version of neural networks. You know, people developed neural net models and neural net controllers, right? Over the last 30 years, hundreds of neural networks. By the way, in Japan, neural networks and fuzzy logic are in every kitchen of Japanese. Every kitchen in Japanese, in the camera of any Japanese, there is fuzzy logic and neural network. In the kitchen, the thing that you do something in the kitchen to produce the meat or whatever, to grind the meat, it's biology, fuzzy logic, and neural network. What you are saying about artificial intelligence is an updated modern version of that. I don't have a model. I have a lot of data, huge amount of data. I let artificial intelligence, machine learning, deep learning, which is an advanced version of neural networks, to do the understanding for me of the data. And based on that understanding, I can predict the behavior of the control loop. So the future is, that's why this is a good question. The future is a combination of data, control, machine learning, artificial intelligence to control this huge, sophisticated, big system through data. Yeah.
Yeah, thank you. Okay, another question?
So Imma Rashid, Imma they understood everything or
yes.
they did not understand anything.
هما حشموا برك حشموا يفوزوا لك الشيخ.
تكلموا إلا بغا بالقبيلية يا سيدي. I don't understand.
Okay, I have another question from another participant. Does brain computer interfaces have place future control systems?
Brain computer interface, right?
Does brain computer interfaces have a place in future control systems?
Of course, yes. This is, yes, brain computer systems were developed some 10, 15 years ago at laboratory level in Germany and elsewhere. And some 10 years ago, it was the very beginning. I got so excited about them that I took three very excellent graduation students, and they did it as a projet de fin d'études here, graduation project. And they developed a brain computer system where they put electrodes in their head, in their brain. The electrodes capture the signal, electrochemical signal from the brain through Bluetooth, send signal to the laptop, and the laptop does the application. What was the, there are many applications. There are applications in robotic, applications in transportation, applications in space, but the application we did is the following. The application we did is in speech. You have somebody who does not talk, and you want to allow him to converse with you, to talk to you. So what did I develop with these three students? We, the person who does not talk thinks in his brain that say, hello, Maamar, hello, Maamar. He says, hello, Maamar. The electrode gets the electrochemical signal, hello, Maamar, goes to his computer and writes for you, hello, Maamar. We did it, we demonstrated in the lab, it gave good results, and there was in Dubai at that time, about 6 years ago, 7 years ago, I used to be young, 7 years ago, there was Dubai, they got together all the Arab countries, all the Arab universities, and present all the projects of students, and my student got the best Arab project at that time. So it was brain-computer interface. You talk and what you thought is in the laptop. This is called brain-computer interface, BCI, brain-computer interface. A lot of research is going on. It will continue. It's a lot of signal processing because the signal that comes from the electrode is very, very, very small because it's coming from the brain. So it's very small. So it's confused with the brain. And hence you have to do a lot of signal processing and filtering to bring the useful signal and separate it from the noise. This is a big challenge. And yes, there are many laboratory prototypes in Germany and elsewhere. Now it's 4 or 5 years. I didn't follow that. But I remember at that time, I printed many books. There are 6, 7 books already in the area, BCI books, brain-computer interface, books of 700, 800 pages in this area doing research and control and signal processing, but mainly signal and image processing plays a major role. But there is one area, one application of BCI is for robot. For robot, somebody does not have an arm through the brain. He wants to do something with his robot arm. And therefore, he can order through his brain to the robot arm. And therefore, there is a lot of control for position and control. And there is a lot of control here, more than signal processing. Yes, this is a big area, robot rehabilitation, robot arm control with BCI. Brain-computer interface.
Alors, il y a une autre question en français.
Yes.
I'm sorry.
Bonjour Rachid, je peux poser une question?
Oui, with great pleasure, Marie.
Yeah. So thank you, Professor Bettayeb, for the nice presentation. I'm sorry I couldn't ask the question because I wasn't muted and I couldn't unmute myself. Okay, so basically, I would like to thank you also for the answer that you provided with respect to the position of the control to respect to the artificial intelligence. However, we hear actually a lot, so I agree that we should kind of build this kind of a synergy between control theory and artificial intelligence, and this is what we are trying to do. But we hear a lot around us that saying, now we can do everything with artificial intelligence. I mean, with all these kind of data-driven approaches, we can solve all our problems. So, I mean, where is the control position here? So does it mean that control now, this classical and standard control theory is dead and we can solve everything with data-driven, or we can still actually build this synergy and there are actually, control is still there and we still actually need it and combine it with this artificial intelligence?
Yeah, that's a good question. Yeah, okay. Artificial intelligence works with data and try to learn from data. That's, if you want to summarize it, that's it. You have a lot of data, billions of data samples, and you want to make sense out of them. That's why there is a whole area called big data. I have a research group in my university called Big Data Research Group. There is a whole area, bachelor, master, and PhD degree in data sciences. So it's all data. Now, what is the contribution of control? First of all, major contributions of optimization problems are from control theorists. So you do optimization, that's one. Two, now, if you assume all you have is data, You may do some control and some with artificial intelligence, you can do what you want, but you have to remember, if you know anything about your physical process and you don't use it, no, you are gonna lose. I repeat, if you have any modeling information about your physical process and you say, oh, I have artificial intelligence, I don't need to get your model to apply control, I will use data, and with my intelligent deep learning, I will do miracles. No, you will not do as good. This is maximum entropy principle. If you have information about your physical system, use it. And by using it, you will improve your control, your signal processing, your diagnosis, your forecasting, your identification, your detection, etc. But if you are in a very noisy environment where you have no idea of the structure of your physical system, yes, artificial intelligence will do many things, but control will never go, because you may be formulated an optimization problem where you are tracking or regulating process variables, and you still have some structures, if not overall, you have local structures that you know about your physical process. You know your physical process is evolving with certain dynamics. Those dynamics, you can translate them into a model or a neural network for which you will develop a controller based on that. So my answer to you is artificial intelligence and machine learning will reinforce the application of control, will be strengthened. Yani, with control and algorithm from artificial intelligence and deep learning, you could do better control.
Yeah, thank you. Another question from Viduhan, thank you. More and more abstract mathematics are less attractive. Do they find their place in control problem or even in the artificial intelligence? Some example, if possible. Give him some examples.
Yeah, well, I can give you many examples. One example is fuzzy logic. When you say right now fuzzy logic, as I told you, it's in South Korea, Japan, everywhere in America. There is a neuro-fuzzy camera. There is a neuro-fuzzy tool in your kitchen. Plenty of this. Now, this, if it was not for abstract algebra, this will not happen. How did it happen? People generalized Boolean algebra that we use daily for our classical control and classical mathematics and classical physics. They generalized Boolean algebra to abstract fuzzy algebra. And based on that, they developed the membership rules, etc., to implement fuzzy logic controller. So it's abstract algebra, which is a generalization of Boolean algebra that made it happen. That's one example, and there could be many other examples. Other examples is sometimes when you solve a theoretical problem, you may be able to understand a physical phenomena. This happened in the US in 1962. There were big professors in Stanford, and at that time, Americans were developing one of the military fighters. And one of the military fighters, they saw that when the fighter goes with Mach 1 speed, when it reaches Mach 2 speed, the fighter goes down and then goes up. You see, the fighter, military fighter, airplane, goes up. When it goes from Mach 1 to Mach 2 speed, it goes up and then it loses speed and then it gains it again. It loses speed and then it gains it again. They could not understand this They never predicted this. They implemented this in the aircraft while they had no theory. So they were wondering why when you go to a certain speed, you go down and then up. Well, some professors, Bryson and famous professors in Stanford in optimal control, they found the solution. What was the solution? It's the theory that gave the solution to the practice. It was done practically first, and then theory explained it. How? They wrote the differential equations, nonlinear differential equations. They solved them, and they figure out that the coefficient, there is some coefficient of Mach 1 coefficient and Mach 2 coefficient. When they flip the differential equation between Mach 1 and Mach 2 coefficient, the differential equation solution went down then up. The position went down and up. And they explained everything, and everything was explained. So this is given as an example in optimal control. I always give it to my student as an example in optimal control that it's physical, practical implementation is better than theory, but sometimes theory helps. Sometimes theory guides you to new discoveries. Yeah.
Thank you. Another question. Alors, dans le cas de la commande via AOIT, le retard, alors, the delay in the AOIT control. What is the problem of the delay?
The problem of delay. It's many. The problem of delay in IoT, first of all, you have a cloud, you have an internet, and there is it's not a physical road. You see, you send data from sensors, and whatever available road, they take it, right? Whatever available channel, they take it. So it's never known in advance. There are thousands and millions of people sending data and receiving data. So your data, when you send it from in the IoT, you will never know the path it will follow, right? Because it's changing, isn't it? It's changing all the time, depending on the queue, on the congestion, on the availability, on the price you pay, on priorities, on security. So therefore, you'll make a delay, and the delay is not known. The delay is random. So that's what makes it difficult. If it's unknown, you may be able to estimate it, but it's variable, time varying, and random. So that's why it's challenging. So you have to develop a new control theory. It's not valid control theory. Smith predictor is not valid anymore because Smith predictor is for control with non-delay. Control with non-delay. This delay in IoT is not known, is random. It changes all the time. It's not known and it's random. It may follow a Bernoulli distribution, or it may follow probabilistically a Markov chain distribution, this delay. And therefore it's not known. So you have classical control theory is not valid anymore. What do you use? Hybrid dynamical systems. Hybrid switch system, hybrid dynamical system. And new theory, all control theory is generalized from classical control to switch control to hybrid control. If you want me to embarrass Professor Rashid, about 10 years ago, I told him, Rashid, we can make an important book and you will become very famous. He told me what? And I wrote for him 15 or 20 chapters of all classical control theory to be generalized to switched control systems. مثلا, classical model, no, switch model, controllability of switch systems, observability of switch systems, identifiability of switch systems, stabilizability of switch systems. And I told him, we'll make 20 chapters and you will be the famous guy in Tizi-Ouzou and in all Kabylie. But, you know, he's busy and we never wrote the book. You remember this, Rashid?
Yes. Another question. Alors, quel est le rôle de l'automatisme dans le domaine médical? Okay. What's the role of the control theory in the medical?
Yeah, but medical now, it's coming in force, where in genomics, in modeling genes, because they have some dynamic behavior, and people are figuring out they follow some nonlinear equations with chaotic or non-chaotic behavior. And now a big development of control theory is in biology, for applications in genetics. In genetics, people are developing, I have seen papers of control and signal processing. People are trying to understand. I have an ex-student who did a master with me here. I helped him to get into MIT, and in MIT, he developed a nonlinear stability theory for biological dynamical systems. Yes, nowadays now, control theory is entering in force in biology to model and control genomics. Very, very important for cells. It turns out there are dynamical systems that follow some nonlinear equations. They have poles and zeros if you realize them, etc. Hundreds of papers. Anybody interested, I can send him some papers, a lot of good papers on control and signal processing in biology with application to genetics, genomics, etc.
Yeah, thank you. Another question from Taurir. Does the vaccine of COVID will not have nanoparticles with which one day we could be controlled with?
There is a lot of talking about this. Listen, now we have many vaccines. The vaccines, they were just produced in 7 months instead of 7 to 12 years. It's well known in medicine. If you want to develop a new vaccine, the average is between 7 and 12 years. I have I am vice chancellor for research, so I'm in daily contact with my people in medicine, and it takes 7 to 12 years to do clinical testing 3 and 4 for a new drug or new vaccine. Between 7 and 12 years. They did it in 7, 8 months. What does it mean? The vaccine could be very good, but 2 things we don't know today from all vaccines. One is what will be the side effect, because side effect can come 1 month later, but they can come 3 years later. That's why clinical 3 and 4 is done in between 7 and 12 years. So you have to observe the next 7 years to see what is the effect of the vaccine. All right, that's 1. 2, because the vaccine is new, how do I know for how long it will last? Maybe it's a vaccine that is good for 2 months, for 7 months. You have to do those 7 years to 12 years experiments or clinical trials to be able to know. And I think you have heard, I think aspirin, after 40 years, they discovered it has bad side effects. And there are many drugs, after 30 years, they discovered they have bad side effects. Now, this does not mean that we should not have these vaccines. As of today, most of the vaccines they were developed, they did not show important side effects. And hopefully it will continue like this. But nobody, including Vachi, can assess and say today that they are 100% safe. But I would say, as of today, compared to the risk, well, they are worth it. We hope they will be safe. At the moment, they are safe. We hope they continue to be safe. These people who did it in Oxford, who Moderna, who Pfizer, who Kada, they have 40 years experience behind them. So hopefully, by prediction, by forecasting, they are estimating that it will continue doing good without major side effects.
Yeah. Another question. I'm Sid. Very glad to hear and now that in our university, we are talking about all on machine learning deep. Learning theory is one thing, But in terms of investment, are you having any support to put in place lab with all the required infrastructure and material?
He's talking about me or about Tizi-Ouzou?
I think Tizi-Ouzou.
Okay. For Tizi-Ouzou, I would say investment in machine learning or deep learning is not big. You know, deep learning, you need Python and few others, and you can do a lot of things. So the investment is not huge. You need some software, you need some toolboxes, and you can work. Of course, you may need a server to do experiments and things like that. But frankly, the investment is not huge. If you want to do applications to robotic, to computer vision, then you may have to buy many robots and things like that. But you can start really. I advise you the following. There are many open source software you can start with. They are free, they are available, and they can do a lot of deep learning. They can do a lot of machine learning. They are available. Just do open source machine learning, open source kada. And there are a lot of open source software available for free. You can start with, and later on, you develop your own, you journalize, you buy another one. Once you get project, you get funding, etc. But yes, it's possible to do with start with small investment. Start with open source software available. It is free. It is there. Get some, maybe a toolbox similar to a toolbox of Python or related, and you can have a good start on developing deep learning and machine learning new algorithm for some specific applications. Yes, you can start very easy.
Thank you. Okay, another question? Y a-t-il d'autres questions? Okay, so I think we can stop here, Professor Maamar.
Barakallahu fikum. Really, it was really a great pleasure being with you. I'm very happy. Many interesting questions. So, inshallah, next time I will come and give the seminar to Tizi-Ouzou, inshallah.
Marhaban bik, Sheikh. Marhaban bik. Every time you will welcome, Sheikh. Inshallah. Inshallah. Okay.
Je vous remercie beaucoup, Cheikh Maamar.
Barakallahu fik, Ridwan. Barakallahu fikum.
Il y a Aïden qui voudrait te dire un mot. Mohamed Aïden.
Oh, Mohamed, mashallah. It's a long time. صحيح محمد. شاك لاباس. خير. راك muted. ايوه.
C'est avec plaisir qu'on te voit, Cheikh.
الله يسلمك. بارك الله فيك.
Merci beaucoup pour la conférence.
Voilà, c'est un plaisir. C'est mon honneur.
C'est un plaisir. Inch'Allah, une autre fois à Tizi-Ouzou.
Inch'Allah.
راحت الشيخ. هيا bon courage.
بارك الله فيك. صحيت. بارك الله فيك.
Ok, donc au nom de Maamar et au nom de Ridwan, je tiens à remercier tous les gens qui ont participé à la conférence, particulièrement Ahmed et Myriam, Fazia et Jafar. Il est muet, il ne veut pas parler, mais bon, j'imagine qu'il se préserve pour la prochaine conférence, Inch'Allah. Donc, c'était avec plaisir, Cheikh.
Shukran, barakallahu fikum. C'est vraiment un grand plaisir et un honneur pour moi d'être avec vous.
Tizi-Ouzou Dardark, Cheikh. Tu es toujours le bienvenu. Donc, j'informe mes collègues.
Il a fait le khotot الجوية cet été. Je viendrai en vacances et je donnerai un séminaire, Inch'Allah.
مرحبا بك Cheikh. مرحبا بك. Donc, je tiens à informer l'assistance qu'il y aura, Inch'Allah, d'autres conférences dans les prochains, probablement après les fêtes de fin d'année. Donc, on a prévu avec Jafar, et je le remercie beaucoup, Jafar Abdel-Slam de l'Université de Mouloud. On a également Hannes Malek, notre collègue de l'École centrale de Nantes, qui a donné son avis pour nous présenter une conférence. Et je le remercie beaucoup. Nous avons aussi Myriam Lalag de Chaos, في مكان في السعودية. Elle va nous faire, Inch'Allah, une conférence aussi. On va essayer de programmer ça au courant de l'année du mois de janvier, Inch'Allah. Voilà les 3 prochaines conférences qui ont officiellement, donc on a qui vont être programmés fin janvier, en attendant donc de contacter d'autres et qu'on programmera avec Radouane et les collègues du laboratoire et du CSP. J'espère que les étudiants en ont profité. Ils savent un petit peu sur quoi le contrôle. La plupart, ils ne travaillent pas beaucoup sur le contrôle parce qu'ils ne savent pas ce que c'est le rôle du contrôle sur la technique. Donc, j'espère qu'ils ont profité. Les docteurs Tewana aussi, s'il y a des questions à venir, ils peuvent m'adresser la chose et je ferai parvenir leur doléance, le Maamar, avec plaisir. Voilà, M. Ardouane, si tu as un mot à dire.
Pas beaucoup de choses. J'aimerais juste remercier tout le monde. Donc, cette conférence est la première probablement d'un cycle de conférences qui va se dérouler tout au long de l'année. Inch'Allah, on va réussir à faire ça avec tout le monde. Et voilà. Et je tiens à remercier ceux qui étaient présents aujourd'hui et j'espère qu'on aura la chance de se revoir la prochaine fois, Inch'Allah.
Et merci beaucoup, Ali Blay.
Merci, Blay.
C'est un plaisir. À votre service.
مرحبا بكم.
شكرا.
بارك الله فيكم. السلام عليكم.
السلام عليكم. بارك الله فيكم. شكرا.
عليكم السلام. عليكم السلام. Allez, au revoir tout le monde.
Au revoir.
Avec plaisir, Cheikh, à votre service.
Merci beaucoup. Ça va, ça t'a plu?
Super, comme d'habitude.
Très bien, ça fait. Dans quelques temps, peut-être en janvier, je ne sais pas si c'est le 6 ou le 7, un mercredi, il y aurait quelqu'un d'autre.
Ah ben, super.
Inch'Allah, ça fait.
On s'appelle, au revoir.
Allez, au revoir. Au revoir.